Hi guys, if you haven't done so already, go to the back of the room and get your water kit. It's a cup and it has this same picture on it. And we will start from there. Alright, review of water. What's the chemical formula for water? I think everybody knows that water is H2O. That's the one chemical formula we all know. Alright, and if you'll get one of the water molecules out of your water kit, you'll see that we've got one oxygen and two hydrogen, and these molecules are going to act like real water molecules. Alright, note hydrogen atoms and oxygen atoms are not really red and white in real life. And it's also impossible to see a single water molecule with the naked eye or even with the most powerful light microscope. Alright, here's a picture of our water molecule, and we're going to go back to first semester real quick and we're going to look at this. We can see that water has two shared pairs of electrons, that oxygen sharing a pair with each hydrogen, and then it has two unshared pairs on it, and therefore the hybridization on your water molecule is an sp3 and its molecular geometry is bent. Alright, here is a picture of a water molecule, and you're going to draw the structure of water, including the charges on your atom, on your paper. So here we're going to note that hydrogen atom has a partial positive charge, and so on your hydrogen, you can see it kind of looks like Mickey Mouse here. And those two hydrogen atoms have a partial positive charge, and then your oxygen atom has a partial negative charge. And because of this partial positive charge and partial negative charge, we're going to see here in a minute that oxygen is polar because of these charges. Okay, so let's look at our water molecule. Oxygen has 6 valence electrons in the outer shell, and of course it needs 8, I8, I full. And hydrogen has 1 valence electron, so it needs 2. And neither atom wants to give up an electron, so they're going to share. So we're going to call this a covalent molecular bond. Alright, although they're sharing the electrons with the hydrogen atoms, the oxygen has the greater attraction for the electrons, so we say it is more electronegative than the hydrogen atoms. So the electrons spend more time near the oxygen's end of the water molecule. And let's watch this happen here. You see how it's pulled towards it. Okay, oxygen atom also has 2 unshared pairs of electrons, so that tends to make that oxygen end more negative. And unshared pairs repel shared pairs and hydrogen atoms off to one side, creating that Mickey Mouse looking shape that we were talking about just a moment ago. We can see that. See that happening there? Alright, let's look at it again. I'll go back and then we'll see that happening. See that, how it gets pulled? Alright, as a result, the oxygen end of the water tends to have that slightly negative, and hydrogen end has that slightly positive charge, and therefore it is a polar molecule. Alright, and I already said oxygen's very electronegative. Okay, we're on question number 5, if you're with me following along on your notes. Alright, molecules such as water that have positive and negative ends are called polar molecules. Okay, and these positive and negative ends are called dipoles. Alright, what do you think will happen when 2 water molecules bump into each other? So here's where you need to get some more water molecules out, and you're actually going to take those water molecules and you're going to bump them together, and you're going to see what happens. Okay, so we're on question number 6 in our notes. What parts of the water molecule will stick together? Okay, so bump them together, and what happens? We're going to get that positive end to the negative end. So that's hydrogens attached to oxygens. Okay, so in reality, water acts just like these magnets inside our models, and the positive end of one molecule will bond to the negative end of the other molecule. So you can see this bonding right here in this picture. All right, now take one water molecule from your kit and see how many hydrogen bonds each water molecule can form. So we've got one water molecule, and how many can I stick to that one water molecule? Okay, let's go back here for a second. How many water molecules did you get to stick to that one molecule? And if you're not sure how to do it, come ask me and I will show you so you can get the answer to number 7. Okay, moving on, we're on question number 8. We're going to allow 2 water molecules to stick together. Okay, now pull the 2 water molecules apart and feel what that, get the feeling of what that feels like. This is going to model a real hydrogen bond in real life. And then now you're going to try and pull a water, not a water, but you're going to try and pull a hydrogen off of a water molecule. Okay, and we're going to figure out which is harder. Is it harder to pull 2 water molecules apart, or is it harder to pull a hydrogen off of a water molecule? Okay, so that's question number 8. Again, if you're not sure, come ask me. All right, we should be there on question number 9. What is the name of the intermolecular force that holds 2 water molecules together? And that force that holds them together is called hydrogen bonding. All right, and you can see here's how you take one of those hydrogens off that water molecule if you need to do that. All right. Now, did you try and pull a hydrogen off one of those water molecules? You're just going to see which one's harder, how much effort is needed. All right. So inside the water molecule, this intermolecular force that holds the hydrogen to the oxygen there, that's a different kind of bond. That's called a polar covalent bond. Okay? And polar covalent bonds are much stronger than hydrogen bonds because it was a lot harder to pull that hydrogen off of that oxygen than it was to pull 2 water molecules apart. Okay, so our stronger bond would be that polar covalent bond, and these are the type of questions that are going to be on the test. All right, so we're on question number 12. Okay, water's ability to hydrogen bond gives water all of these special properties. So anytime I'm asking you a question about why does water have any kind of special property, your answer is almost always hydrogen bonding. So here, water has high surface tension. Why? Hydrogen bonding. It has low vapor pressure and high boiling point. Why? Hydrogen bonding. The solid state is less dense than the liquid state. Why? Hydrogen bonding. High specific heat. Hydrogen bonding. Universal solvent. Hydrogen bonding. Okay, so this throughout the notes it's going to ask you, why does water have this ability? And that is your answer, hydrogen bonding. All right, moving on. Okay, what is high surface tension? It's an inward force that tends to minimize the surface area of a liquid. It causes the surface to behave as if it were a thick skin. So think about when you put water in a glass, or later when you do this water lab, you're going to see that water will bulge over the top, or form brown drops, and all of this is because of surface tension, which is created because of why? Hydrogen bonding, okay? Look, and we see, why do things float on top of water? Or why does water form beads? Again, hydrogen bonding. Here's some good examples, and we're going to do some of this in the lab. Okay, one water molecule hydrogen bonds to another, and it occurs to all the molecules all around. And so each water molecule can bond to 4 other water molecules, and that was your answer to that question that's back there in number 7 if you did not figure that out. Okay, a water molecule in the middle of solution is pulled in all directions, but that's not true at the surface of the water. It's only pulled down to each side, and it holds those molecules together, and it forms kind of a skin, which causes this surface tension to happen. All right, why are water drops round? Because all molecules on the edge are pulled to the middle and not pulled into the air. All right, here's some more examples. Glass has polar molecules, and glass can hydrogen bond, and it attracts the water molecules, and some pull it up into the cylinder. So if you're putting something in a graduated cylinder, we get what we call the meniscus. If I tell you, how do you read a graduated cylinder? You read from the bottom of the meniscus. What's a meniscus? It's the curved surface that occurs when you put water in a container, like a test tube or a beaker, okay? This does not happen with plastics, okay? So here we can see what happens if I put water in a glass test tube versus a plastic test tube, okay? A meniscus is the curved surface that occurs when you put water in a container. Okay, that's your answer to question 16. All right, all liquids have some type of surface tension. Water, though, is higher than most others. But what if I want to decrease the surface tension? What am I going to do? I'm going to use a surfactant, which is a surface active agent. What is a surfactant? It's a wetting agent like detergent or soap. And what does that do? It interferes with the hydrogen bonding. That's why we have to put soap in the washer, or soap when we wash dishes. Okay, so what do these do? These surfactants lower the surface tension of water by breaking the hydrogen bonds of the water, essentially making it wetter so that it's less likely to stick to itself and more likely to interact with oil and grease. Basically, soap allows oil and water to mix so that oily grime can be removed during rinsing. And look at our picture here. You can see that happening. Okay, low vapor pressure and high boiling point means water needs a lot of energy or heat to make it evaporate or boil. Okay, and why does that happen? High surface tension. Okay, and it's a good thing. Water has low vapor pressure, or lakes and oceans would evaporate really quickly, and what would happen? All of our sea life would die. Okay, water's ability to hydrogen bond gives water all of those special properties. Again, why does water have high boiling point or low vapor pressure? Ability to hydrogen bond. All right, ice. What happens when water freezes? Okay, so most liquids contract or get smaller as they are cooled down. And they also get more dense. When they change to solid, they are more dense than the liquid state. So for an example, solid metal,